So she is a professor at the University of Abuja in Nigeria, and she's interested in algebraic topology, if I'm not wrong. Algebraic combinatorics and group theory. Yeah, sorry about that. So she's from the University of Abuja in Nigeria and interested in algebraic combinatorics and group theory. Okay, so today she'll be talking about structure of subgroups of finite semilattices, that is symmetric inverse semigroup. And she shared her abstract early on, which I'm going to paste on the chat in case someone is interested or they did not see it. Okay, so yeah, you can start, please. You can start.
Okay, thank you, Nazreen. Thank you, everyone. So I'm here to present a seminar with the topic structure of subgroups of finite semilattices using symmetric inverse semigroup. So the outline of this seminar is as follows. The preliminaries, we're going to look at the method. We use Stirling number of the second kind and Euleria number. Then the results, that's constructing the structure of n other subgroups of finite semilattices. And then, so the abstracts. Okay, so the abstract is that we let X be a finite set of endpoints and it is non-empty. We define symmetric inverse semigroup denoted by ISN, and we use the semilattices of idempotent built on this symmetric inverse semigroup. And we obtained subgroups of identities of order 1, and we also were able to determine the cardinalities of 2-element subgroups using Stirling number of the second kind. So there are some definitions which are necessary in this seminar. And I know some of them, we might have heard of them or seen them, or we might have been using them, but it's a way of reminding ourselves because of this seminar. So the first definition here is groupoid. Groupoid is defined as a non-empty set on which a binary operation, which is used as this, we use mu to denote it, and the binary operation mu is defined. And then, so if we want to use this to define a semigroup is defined together with the groupoid. The operation mu is associative. That is, a semigroup can as well be called an associative magma, because a magma consists of a set equipped with a single binary operation that must be closed by definition. So these are two ways of defining a semigroup. Another definition is transformation. We use the notation alpha with this example in general. A transformation can as well be known as a function or a map, and it's an array that has domain and then codomain. So each of the points in the domain has a value. So as it can be seen here, we use ki to denote the value for each element in the domain. So the element ki is called the value of the transformation alpha at the element x. And the usual notation is, if I want to talk about the value of x1, I use alpha x1 is equal to k1. And that is as well known as the image. That is, the image of x1 is k1, the image of x2 is k2, and so on like that. Then Now, transformation semigroup is a collection of functions from a set to itself that is closed under function composition. So we use this pair to denote transformation semigroup. And usually we use just S. Once the semigroup is identified, we use S to denote the semigroup under discussion. Then identity is the usual definition of identity, as if we have for every element X in S, X1 is equal to 1X and is equal to X. That is the identity. And there is something, the reason why this definition is coming up here is to show that any semigroup that has or that contains an identity is called a monoid. So then, okay. So the next definition, the symmetric inverse semigroup, and that is the semigroup we are using. There are many different types of semigroups that many researchers have used to, to work on. We have full transformation semigroup, partial transformation semigroup, partial one-to-one transformation semigroup. So the one we are using is partial one-to-one transformation semigroup. But partial transformation semigroup is like a mother to all the semigroups you, at least for now, can talk about. So the partial one-to-one transformation is also known as partial injective transformation semigroup. And the usual name for it is symmetric inverse semigroup. And it means partial bijections. And what this is saying is the domain is a subset of the finite set defined, and as well the image is also a subset of the finite set defined. And the cardinality of symmetric inverse semigroup is as seen here with the cardinality of the idempotent, which is 2 raised to n. Then semigroup ISN is orthodox, which means it's a regular semigroup whose set of idempotents forms a sub-semigroup. Not all sub-semigroup or not all subsets of a semigroup form a sub-semigroup. And at the same time, not all idempotents form a sub-semigroup. But in this particular semigroup we are using, the set of idempotents forms a sub-semigroup. And this more unorthodox semigroup can be seen in Higgins and Owens' work. And as well in their this work, we can find standard notions and notations on semigroup. So a semilattice is a structure denoted by this, where the dot there is a notation for binary operation, which is associative, commutative, and then for each element in this particular set is each element is an idempotent. So if all these three properties are satisfied, then we call that a semilattice. So the semilattice of idempotent mappings, we use E to denote it. And semilattice of groups is the intersection between two fundamental classes of algebraic semigroups, namely inverse semigroups and union of groups. So the work by Grillet communicated that any inverse semigroup can be constructed in terms of its semilattice of idempotents and a number of groups. So this one per D, it's green. We have what we call the Green's relations, and D class is one of them. We have the R class, the L class, the H class, J class, and then D class. So Preston defined inverse semigroup to be a semigroup of all bijections between subset of set X. And so the one we are now looking at, as I earlier mentioned, is the symmetric inverse semigroup. So we need to also define subgroup according to this study. So if we let S be a semigroup and H is a subset of S, then H is a subgroup if it is a group under restriction of the binary operation with the following properties satisfied. So it is closed. That is, if we have these two elements in H, the binary operation is such that it is closed in H. And then the identity in H is defined in this form. And the identity here does not mean 1. The identity 1, as we may be expecting, no, but it's an idempotent. So we have this defined, and then we have for all A in H, there exists B such that the inverse, that is, 1 is the inverse of the other. But in this particular study, the inverse, that is, the inverse of an element is itself. So the following are some remarks we need to just take note of. The proof of the user, the number of ways of partitioning a set of n elements into m non-empty sets. For example, if we have a set of 3 elements or 3 points, as we can see here, if we want to partition it into 3 subsets in one way, so we have just 1, 2, 3. So if we want to partition into 2 subsets, we have it in 3 ways, as we can see here. And if we want to partition into 1 subset as an entity, it happens in 1 way. And this is defined or discussed by Riordan and then Roman. So, and then the notation for Stirling numbers as known is this. So there are 2 sets of numbers that bear Stirling number. It's their Stirling name, Stirling numbers of the first kind and second kind, but here we are using Stirling numbers of the second kind, and it is easily computed, or we can compute the numbers using this expression, and as we can see it here. So the Eulerian numbers on the other side count the number of permutations of fixed size with a given number of increasing runs. So, and for any permutation, we use 1-line notation. The example I used previously, we used 2-line notation here. So this is 2-line notation. But here in Eulerian, to count the number of descents, we use 1-line notation. And it's basically the image, that is the image as it appears in the element. So, and the symmetric group, which is denoted by Sn, we use 1-line notation, and here we count the descent. That is, a descent is a position such that if we have W of I is greater than W of I plus 1. So these are descent, that's talking about the position of each point in the 1-line notation. And it is such that the position, if you look at the numbers in the position, the image, if the image preceding is greater than the one after, so we say that it's a descent and we count it. So look at this example now. If we let W be an element, you can see that the descent here is 3, because we have 6, 5, 5, 2, and then 2, 1. So we use this to denote Eulerian numbers. Now, but here we are using Eulerian numbers in symmetric inverse semigroup. And in this work, the K here that counts number of descents is 0 using the Eulerian numbers. But when we are using it, the K is going to be 1, because that is the column for Eulerian numbers for k is equal to 1, and that is the result we're able to obtain. So now let's see the structure of n other subgroups of semilattice. So we obtain j element subgroup sets where j is equal to 1 and 2. So for the remaining j's, this is just part of our research work. So, and we should also take note that in semilattice, commutativity is ensured, and then the elements have to be idempotent. So now let's look at the following theorem on zero elements. So the zero element is defined. That is, we say that an element is a zero element if there exists another element in the set. Let's denote the element with alpha, and there exists another element beta, such that alpha beta is equal to alpha and is equal to beta alpha. So it means both elements are left identities, and one is the zero of the other. So now, if we let alpha beta be in the idempotent of highest n, then alpha is a zero of beta if and only if alpha is less than beta. And the proof of the theorem is as follows from the definitions of zero elements. So it means the two elements are identities, and the semigroup, which is, remember we said that the set of idempotents of an even semigroup form a sub-semigroup. So in that case, E is a semigroup of finite identities, which has finite number of zero elements, as it can be seen. And then the domain of alpha is a subset of the domain of beta. And in that case, it can see that this satisfies the fact that alpha is a zero of beta. Then look at this one element subgroups. One element subgroups is just trivial, as we know that when we're talking about a subgroup, it's such that the element is its inverse, its identity, and if you are looking at the closure, it is closed, so it's trivial. And like I already stated, that the empty map is excluded. So looking at the cardinality of ISN given earlier and the cardinality of the idempotent of the symmetric inverse semigroup. So if our n is 3, so it means the E of IS3 is going to be 7. And it means we have 7 one-element subgroups of this semilattice. So 2-element subgroups can be seen as defined. So this is a subgroup. So we have them 2-element subgroup. So, and so we have the following theorems to generalize n-element subgroup. First and foremost, the maximum subgroup, the semilattice of the symmetric inverse semigroup can have is n. That's the maximum subgroup. So if we're talking about n is 3, that means the maximum subgroup it can have is 3 elements. That's a set of 3 elements. And the proof is the 0 elements of a subgroup is a non-empty map. And if the 0 element of a subgroup is a non-empty map, we define our 0 element here not to be empty because we exclude. But if we find composition of 2 0 elements as defined here, it will produce an empty map. So which is contrary to the exclusion of an empty map in this study. And that is the reason why the maximum set of elements is subgroup of A, the idempotent symmetric inverse semigroup can have is n. So then it is very important, like I stated earlier, we saw that, okay, one element structured subgroups, how many of it do we have? So we have 2 raised to n minus 1. And, this is combinatorial in nature, so it can as well be expressed in this form. So that is the proof of this theorem. So we have 2 raised to n minus 1 element structured subgroups. Then if we have let E be the semilattices of ISN and P be the order of subgroup. So E has n combination P structural subgroups for P is equal to n, 2 to n, where n is greater than or equal to 2. So the structure has to do with knowing the number of elements that makes a set to be a subgroup. So the proof of this is an application of binomial theorem, and we use the coefficient, but using the coefficient is with a restriction. We excluded P is equal to 0 and 1 for each n, and so we combine the length of image as subset of n, and then with the exclusion of an empty map, and then we have the result. So we now want to derive a closed formula for the element obtained in each of the structures. We have seen the number of structures that subgroups, that is semilattices of ISN, can have in terms of its subgroups to be n combination P. So we have this. So, and for instance, now we said that if n is 1, so it can only have one 0 structure, that is like 2 raised to n, 2 raised to 1, 2 minus 2, that's 0. And that is why we said that P should start from 2. So it means n starts from 2. So if n is 2, that means the structure is just going to be 1. If n is 3, it means the structure is going to be 5. That's 8 minus, okay, it's going to be 4 rather. So that's 8 minus 4. So sorry. So now, having known that, we now want to derive a closed formula for the element obtained in each of the structures. And that is when we introduce the m following factorial. So the m following factorial is defined as follows, as you can see here. And so let's see the following proposition and lemmas before the theorem. So if we let m equals 2, using the following factorial, we have this. So n, that's the m is 2, and then we choose 1. So the proof of this is seen as follows. You let H be a subgroup, and alpha, beta are the only element of H because it has 2 elements. So we have the image of beta is strictly contained in the image of alpha. So it means that the composition of alpha beta equals the image. That is, if we look at the composition of alpha beta, the image is equal to the image of beta. And if the image of beta is not contained in the image of alpha, then it means the 2 elements are not in the subgroup. So we obtain a sequence using this. And this sequence, of course, is in the online encyclopedia of integer sequences with this number. And this number is known as a heteromessic number or rectangular number. So now we have some lemmas for when m is 3, when m is 4. So, and so we have, so this each of these generates a number, a sequence. We have a sequence generated by each of these. When m is 5, you choose 4. When m is 5, choose 3. So we have when m is 6, we choose 5, 4, 3. And you can see that the numerator is talking about the Finite factorial. We use that notation for it. So, and then we have the following from that theorem, the theorem that talks about the number of structures of the subgroup of the semilattices of symmetric inverse semigroup. So this then, so that table it's talking about the number of structures, and this is it. And this is the Eulerian number when k is 1. So this is the Eulerian number, that's n choose p, as we can see here. Now, the theorem that now talks about the subgroups of ISN. So if we let the set of idempotents be denoted, that is E of this, which happens to be the subgroups of the symmetric inverse semigroup, then the cardinality is the Stirling numbers of n, k is 3. In this case, we use p, and so we have p, 3. So in Stirling numbers, it should be n, k, but due to the notation we employed, and to avoid confusion, so we have a p, 3, and this is one of, if you look at Stirling number of the second kind, this is when k is 3, if you compare, but it's not when k is 3, because we have to multiply the Stirling numbers by 2 to give us the subgroups of symmetric inverse semigroup. And so the proof of this is we used the Stirling numbers of the second kind and the proposition 3.5, lemmas 3.6 to 3.9, and to prove this particular theorem. So, and we have the elements denoted by Q, that is, we split the elements into Q ways to form a group, and we also made use of the proposition 3.5 proved earlier to talk about the number of subgroups when m is 2. So we made use of that, and then the lemmas to show the number of elements, that is the number of subgroups of symmetric inverse semigroup. So if we take note of this, say that lemmas 3.6 to 3.9, there are 2 element subgroups, because those lemmas proved basically on 2 element subgroups, and it has n-1 combinations, with each combinations forming a column of values for each n. And this is obvious, the 2 values partitions of n, they are equal. And then we also made use of the binomial coefficients, and it serves as the initiators on which other values are built. We made use of the fact that since n is greater than or equals to 2, so the n for the values for n equals 0 and 1 are 0, and that is why we didn't include that in our derivation of formula. So the Finite factorials with some missing terms, they are the numerators, and the denominator is determined by deleting other values in the binomial coefficients, which when we sum together gives Stirling number of the second kind as given here. And this is the table. This is just part of the 2 element subgroups of semilattices of ISN. as it can be seen. And, you know, like I said, this is just part of the research that is still ongoing. So we hope to now find the generators for this semigroup, that is for this the subgroups, because we have seen the one element subgroups, we've seen the two element subgroups, we already have all other subgroups. Then it's now left to come up with a formula or a way such that we can generate, that is, we can have a set of generators for all the subgroups, irrespective of what n is. So the conclusion is that the structure of the subgroups of semilattices of ISN was obtained, and then we summarize the structure using Eulerian number, and the cardinality of subgroups of order 2 was derived using Stirling number of the second kind, and we also showed some results that form part of the closed form formula for constructing all finite semilattices of groups. So the references are as follows, as you can see here. So thank you for listening.